Welcome back. We are starting the first of three sections that involve something called a power series. And this entire chapter has been building up to exactly this. This section is an introduction to that. The next two are specific ways to create power series. And let's talk about what they are. They are actually polynomials. Now, I want to be clear, there are two variables going on here. We have n that is doing the counting, and then we have x, which is actually the domain of it. This is actually a function of x. It's actually a polynomial, can you see? It's a polynomial of infinite degree. The point of power series, which we won't get too in depth for this particular one, but what we do, where we're going with this, is we want to be able to rewrite other functions as polynomials. So in the next couple of sections, we're going to be taking a function and then turning it into a polynomial and then determining where it's convergent and where it isn't. Now, this particular power series is centered at 0 in this case. Meaning this polynomial will most accurately represent whatever function this came from. It'll be the most accurate at x equals 0. And the further from 0 we go, the less accurate that is going to be. Now, the c's that you see here are constants. These are specific numbers as coefficients are here. And this power series is centered around the letter a. So you can see that's x minus 0, say. And here it's centered at 0. Here it's centered at a, pardon me. Here it's centered at a. So at x equals a is where this power series is going to be the most accurate as far as it representing another function. Now, when I say another function, I mean like a logarithmic function, an exponential function, a trig function. So functions that aren't necessarily as easy to deal with if we're talking about an integral or a derivative. But as we all know, derivatives of polynomials are very, very easy to do. So we are going to take a step back. I'm going to show you some notes from a previous video. And we are mostly going to be using the ratio test to determine which values of x are we allowed to use so that it is convergent, ideally. Now remember, that means that that limit has to be less than 1. So as long as we can find values of x's where that limit is less than 1, we are good to go. If we can't, then we say that it's divergent. And when it equals 1, when this limit equals 1, then it's inconclusive. That's actually when things start getting a little interesting, actually. And we'll come back to that. So let's move on to our first example. We want to know which values of x is this convergent. And again, we're going to use the ratio test. We can use the root test because that has a similar feel to it, but for the most part, we're going to do ratio. And this is going to be n plus 1 factorial, then x to the n plus 1 over n factorial x to the n power. And what I'm going to do is I'm going to rewrite some of this like this. And we can clearly see the n factorials dropping out and the x to the n's reducing out. Now the x variable has nothing to do with this limit, so I'm going to actually pull it out in front. And we have a problem. This limit goes off to infinity. And infinity times our x is going to give us infinity. Once again, back to the ratio test. If that goes to infinity, then it's divergent. Therefore, our summation n equals 0 to infinity, n factorial of x to the n, is divergent everywhere except for divergent for all x except when x equals 0. And I want to show you what that's going to look like here. Do you see if we go back to the original, we get, if x is 0, then we get 0 plus 0 plus 0 plus 0 plus 0. So we say it's divergent everywhere, but we want to mention the exception that when x equals 0, it's not divergent, it's actually convergent. But when x exactly equals 0, who cares? That means that this function is completely useless here. So let's go on to here. And which values of x is this series convergent? Once again, we're going to use the ratio test. Remember, it's that divided by that. So I'm going to multiply by that, I should say. And so instead of dividing it, I'm going to multiply by the reciprocal. All right. So I'm going to break that down. And I'm going to note x minus 3 to the n power reduces out. By the way, just a quick side note, this power series is centered around the number 3. So that's more like this here. And we are left with, again, the x has nothing to do with the n. And we have the same degree in the top and the bottom. So this limit here goes to 1. Now, what that means is we are left with the absolute value of x minus 3. And what we need to be convergent is for that limit overall to be less than 1. So we're going to say is less than 1, because that's really what we're interested in. So this means that we're there, and when I add 3, so now we're here. So we have our interval when x is convergent. So these values are when our power series is convergent. But we have a small problem. When the limit equals 1, we have a problem with that because it's inconclusive, meaning we don't know what happens at x equals, when that limit equals 1. So what we're going to do is I'm going to plug in, because we don't know what happens at the endpoints, right? When x equals 4, 4 minus 3 is 1. Ooh. When I plug in 2, that's 2 minus 3, that's -1. Absolute value is 1. Ooh, that's that inconclusive one again. So what we're going to have to do is test each of those endpoints. So we'll start here. So test the endpoint. So at x equals 4, now I'm back to here. Now here's the problem. 4 minus 3 is 1. 1 to any power is always just 1. So that n is now irrelevant. And this is a p-series. It's specifically a divergent one. So what we have is that we are not going to include 4. Now, let's test x equals 2. That's the other endpoint. You see 2 minus 3 gives me negative 1. So now we have this. Now this is an alternating series. Where b sub n is 1 over n, which is decreasing, and the limit, as n goes to infinity of 1 over n, is 0. So this converges by the alternating series test, which means 2 is included. So you can see one of the endpoints was included, the other one was not. So we say that the interval of convergence is here. 2 is included, 4 is not. So these are the values of x for which this converges. Now there's one other piece of information that we can get. If we go back to here, and that'll be 2, that'll be 4, that'll be 3. We're centered at 3, right? There's the 3 there. What we can look for is something called the radius of convergence, meaning from 3, how far away from 3 can I deviate in both directions? Do you see? I can deviate a distance of 1 from 3 in both directions. So we say that the radius of convergence is r equals 1. So there is our first big one. Now, we are only going to have to test the endpoints when that limit goes to 1, or to a specific number, I should say. All right, let us move on. All right, this is actually a famous function. It's called a Bessel function. It has to do with harmonics and music and things like that. And so what we're going to do is we're going to do the ratio test once again. And see what we get. Now, again, because the absolute value, the negative 1 is now irrelevant. So when n turns into n plus 1, I have to distribute the 2. That's where I get the plus 2 from there. Same here. And I'm going to make that n factorial times n factorial. So this is going to be n plus 1 factorial times n plus 1 factorial times the reciprocal of that, n factorial times n factorial times 2 to the n over x to the 2n. All right, so I'm going to break these two down, and I'm going to break those down as well. This becomes x to the 2n times x squared times n factorial times n factorial times 2 to the n over, this becomes 2 to the n, 2n, pardon me, times 2 squared. That should be 2n there, 2n. And then this becomes n plus 1 times n factorial times n plus 1 times n factorial. And we got a lot of juicy stuff reducing out here. X to the 2n is gone. Oh, I forgot that. X to the 2n. down here. Sorry about that. And that reduces with this here. 2 to the 2n, gone. N factorial, both are gone. And in the aftermath of the bloodbath, we have absolute value of x squared up top. Down below, we have 4 n plus 1 squared. To be clear, again, the x and the 4 have nothing to do with n. We are there. And I'm hoping that you can see as n gets really large, this whole piece here goes off to infinity. And infinity times this is going to be infinity. I'm sorry, that doesn't go to infinity, that goes to 0. The denominator goes to infinity. So that goes to 0. And 0 times who cares is going to be 0. Here's the cool thing about this one. This will always be less than 1. So in this case, this converges for all x, meaning negative infinity to infinity is our interval of convergence. This is the best case scenario for us. This means we can use any value of x as long as we shove n off to infinity. This will represent the function that we are interested in. All right, so as we're looking at this Bessel function that we just showed is convergent everywhere, I thought it'd be a good idea to show you sort of a picture of what we're talking about. So if we iterate this out, and we're using i's instead of the n's in this case, and we're doing it the partial sums, meaning we're stopping at a specific number. So we can see the Bessel function, that's the j here, that's this one here as it's coming down here. And you can see this parabola is not anywhere close to that, but here, very close, it is. Now, I want to point out that this Bessel function is centered at 0. If it was x minus 5, then we would say it's centered at 5, but it's just x. So we're centered at x equals 0. And you can see all of these other functions are the most accurate right around here. And so the second degree one, you can see that parabola is there. You can see it's negative coefficient. It's headed downward. And then all of these other, you can see are, as n is increasing, 6th power, 8th power, you can see that we are getting further and further away from 0 and still holding a good amount of accuracy as we're doing that. So that really is the power of power function, is its ability to do that. And so even if I go to here, you can see I'm pretty darn good from about here and everywhere in between. So I could use this function, this polynomial here, to represent my Bessel function up to a certain tolerance, right? And you can see if we kept going, it would get more and more and more accurate to the Bessel function itself. So that's sort of what's going on here. Now, our theorem here we have a power series centered at A in this case. There are only 3 possibilities. The series converges only when x equals a. That's that first scenario that we did where it's divergent everywhere except what makes that 0. In that case, it would be a. In the case of the previous example, that was 0 itself. The series converges for all of x. That was our Bessel function for all of x. Our third possibility is that there is a positive number r such that the series converges as long as we are within the radius of convergence. And I talked about that before. And so that's going to be the distance from the center that we're going to be going. So we had 3 scenarios, and we did all 3 scenarios. The first one was this divergent one, where only at one trivial place did it converge. The second one, it converges everywhere. That's like our Bessel function up here. And then this is like example 2, where we have to test the endpoints and all that kind of stuff. All right, let's do a few more. See what we get. All right, so I'm going to use the ratio test once again. I'm going to actually rewrite this. No, we don't need to. You know when we take the absolute value that we don't need that negative anymore. That part goes away. So let's do the limit. So 3 to the n plus 1. Notice I dropped the negative because of the absolute value. X to the n plus 1 over the square root of n plus 1 times the reciprocal of that. Oh, this should be 2. Right, n plus 1 plus 1. And I'm hoping that we can see 3 to the n's go away, x to the n's go away. And I'm left with absolute value of 3x of the square root of n plus 1 over the square root of n plus 2. And what's going to happen is this limit here, because the lead degrees are the same, turns into a giant 1. So we get the absolute value of 3x. And for it to converge, this whole thing has to be less than 1 for convergence. So this means negative 1 divided through by 3. So here's our interval. And we now need to test the endpoints. So let's do that. So at x equals, we'll do negative 1/3. And again, I'm going to plug that into here. And I'm going to bring that negative down below. And I'm going to say that negative 3 to the n over negative 3 to the n reduces out, and I'm just left with 1 to the n up top. And so that is going to give us, it's not even alternating. It's still just 1 over square root of n plus 1. And I now need to determine when, is this convergent or is this a divergent series? Well, I'm going to compare it to one over root n, which is divergent by p series. So let's do the limit comparison test here. That is exactly equal to 1. So it's a good comparison. Therefore, that is divergent. So x equals negative 3 is not an endpoint. We're not going to include that as part of the endpoint. Let's try x equals a positive 1/3. That's the other endpoint. Now I'm going to break this up into this. The reason I'm doing that is so that we can clearly see that the 3 to the n's go away. And that leaves us with negative 1 to the n over root n plus 1. And now we need to determine if this is convergent or divergent. If it's convergent, x, the endpoint x equals 1/3, isn't going to be included in the interval. Otherwise, it won't be included. Now, this is an alternating series test where b sub n is 1 over root n plus 1, which is decreasing. The limit is 0. Therefore, this is convergent. So what does that mean for us? That means that our interval of convergence is negative 1/3, not including the negative 1/3, to 1/3 where we are including the positive 1/3. And to be clear, this is centered at 0. And so the radius of convergence is a distance of 1/3 in both directions. So the radius of convergence is 1/3. There's our interval of convergence and our radius of convergence, which is what they were asking for. All right. Next up. Same question, find the radius and interval of convergence. So let's do the ratio test. Let's see, that'll be n plus 1, x plus 2. So we're centered at -2 in this case. It's always the opposite sign. So I'm hoping we can see 3 to the n is gone. And actually, the 1 reduces with the 2, so it's just going to be 3 to the first power. That is gone as well. And in this aftermath, we have the limit as n approaches infinity of absolute value of n plus 1 times x plus 2. I have 1 left over 3n. That gives us absolute value of x plus 2 over 3 of n plus 1 over n. We can see the degree on the top and bottom here is the same. This whole thing goes to 1, which means this has to be less than 1 to be convergent. All right, I'll knock the 3 over. Subtract the 2. There is our interval of convergence, and all we have to do now is test the endpoints. So we'll start when x equals -5. I'll plug that into here. Now, -5 means that that's going to give me a -3 to the n. I'm going to break that -3. So -5 plus 2 is -3. And so I broke the -3 to the n into a couple of pieces here. And I'll break into that there. All right, so this is looking to me like The 3 to the n's go away. So I'm seeing a 1/3 summation n equals 0 to infinity, -1 to the n times n. That is divergent by the test for divergence. Meaning that goes off to infinity. Plus and minus infinity, actually. So -5 is definitely not one of our endpoints. We're not going to include it as our endpoint. How about x equals 1? You see that 1 plus 2 is going to give me 3 to the n. That gives me n times 3 to the n over 3 to the n times 3. I'll do it that way. 3 to the n's reduce out. We are left with here 1/3 summation n equals 0 of n. And this is divergent for the same reason. That limit of n is going to go to infinity. This is divergent by the test for divergence. So we're not going to include either endpoint. So what is our conclusion? The radius of convergence. Oh, no, we'll get to that. The interval of convergence is -5 to 1. Now the radius is a little more complicated. Remember, our center is at -2. So this radius to me looks like it is a distance of 3. So our radius of convergence is 3. I know these seem like they're taking a long time, and they do. So you just have to kind of be patient. So we have our last 2 problems. Let's see what we get. So we'll do the ratio test again. X minus 2 to the n. And I will notice that that reduces there. We're left with one of them. And I know this looks awkward with all the plus ones and stuff, but if I FOIL that out, do you see I'm still going to get n squared over n squared? We don't care about the rest. The point is this whole part goes to 1. So we get that absolute value of x minus 2 needs to be less than 1 because of the ratio test. So this means -1, x minus 2, +1, add 2, so I get 1 and 3. So once again, we're going to test the endpoints. So let's switch colors again. When x equals 1, when I plug in 1 there, I'm going to get 1 minus 2, that's -1. And so that's -1 to the n over n squared plus 1. And that is going to converge. And that converges because of the alternating series test, where b sub n is 1 over n squared plus 1, which is decreasing, and the limit is 0. So we're going to include 1. However, at x equals 3, we might include it as well. I say however like I know. 3 minus 2 is 1. 1 to the n is just 1. And this gives us 1 to the n, which again is just 1, n squared plus 1. All right, a couple of ways we can go with this one. We could do the integral test. You can see that integral goes to inverse tangent, but I'm going to compare it. So I'm going to compare this to 1 over n squared, which we know is convergent because it's p series. And if I run the limit comparison test, it's going to be that over that. So that's going to be n squared over n squared plus 1, g plus 1. And because this one converges, this one also converges. Convergent. So we're going to include both 1 and 3 as endpoints. So our interval of convergence becomes 1 and 3. Our radius, remember our center in this case is 2, you can see it right there, 2. And that radius is clearly just a 1, a distance of 1. So the radius of convergence is 1. Now I mentioned for this next one that we can, instead of the ratio test, we could use the root test. When would you choose to use that? Specifically when you have to the n to the n. So here we're going to use the root test. This becomes the limit as n approaches infinity of the nth root, the absolute value, x minus 2 to the n over n to the n. By the way, you could try doing this using the ratio test. It's going to get really, really messy, really, really fast. And to the nth powers, all those n's go away. We just end up with the absolute value of x minus 2 over n, which is the absolute value of x minus 2 times the limit of 1 over n. As we all know, that limit goes to 0, which means this entire limit goes to 0, which is great for us. This means that the all real numbers is going to be our values of x that we can use. So the interval of convergence is negative infinity to infinity, because that is always going to be less than 1. And the radius of convergence doesn't really apply here. I guess you would say r is infinity, but that doesn't really have meaning as far as we're concerned. That's a parenthesis there. So that was an introduction to power series. Hopefully that made a little bit of sense. Hopefully in the next few sections, it'll make a lot more sense. Thanks.